I'll talk about the phrase. I did the entire deck last. I did that 2 days. Submitted. I'm gonna do mine about the time I was a Chester. How I was. Good morning, Western High School. Actually, you are in the hallway. Please stand for the pledge of allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Are you interested in free dress for students who wear the homecoming on October 8th? Stop by room P104 during your return periods this week and next week to see if there are anything that works for you. Staff members and marketing students who are planning on attending the Washington Standards field trip should make sure that their permission slips and payments are turned in by Friday, September 30th, in room P104. Attention students who have a hearing loss with a 504 or an IEP. Be free sign from you. We want you to our academic board. There are no fees, dues, or costs. This year, our regional competition is an online activity. Please place your registration on Tuesday, October 4th, in the fees at 3:15 with Coach Post. Juniors and seniors. Our representatives for today are Maryland University, St. John's University, High Point University, and Maryland University. All sharing in the
Argon, and then 5 is 2. Argon, you were Argon is a green.
Are you gonna talk about no, it's fun. It's fun. So the first experience
Not correct. Tip 2. See where Argon is? Argon's right here, right? So that's period 3. After Argon, come down to 4. So it's 4 is 2. It jumps all the way down to 5. Right? So this would have to be Krypton. It's like Krypton, this would be right.
No, it's funny
Okay, gotcha. I'm gonna get you on camera.
That's such a good.
Anyone else need a?
I do that. No, then no. I do that every. No, I do that now. I don't. I just showed my. Saying I manually grab water. I know how I actually, I shoved my. I grabbed
3, 10, 4, 6, and then 5 S2. So this should have the next level gas. She comes by. So Yeah. No, I can't see your work. Okay, welcome back. There are technology issues. Gotta love technology. Gotta love technology. So I'm using old school document camera. So yes, my fingers are ginormous. And as you can see, there's still some document technology issues, but we will persevere. Yes, there's not much on the card today so far, but we will add to it. Hund, off-bow, and poly. Hund, off-bow, and poly. You may see them on a ceiling tile. That pink ceiling tile. You also see the names right above. Everyone find it? Hund. I guess that goes Hund, poly, off-bow. Hund, poly, off-bow. So that is the big ideas for today. Another big idea is everyone's babies in the, where's 4? Where are your babies? No, okay. And everyone's babies put in the, put your babies away. I didn't check this. Not the closest one we got. And 8 and 4. No, this was wrong. Okay, so what do we do? We're at lead. So we're all the way there. So look at the periodic table. And we're going for 82. That's lead. So we got to go all the way down. That's 1s2. Right, and then 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, then what? 4d10, then what?
5.
Yep, then what?
6s2.
Yep.
3.
Nope, 6 minus 2. 6
Oh, yeah.
minus
4 at 14.
okay, so you're at 6s2, right? So you have to add what you just said, 4f14, right? And then we're back up here. Then what d is this? 6, you're going to subtract 1, right? 10. And then 6, P1, P2. Right? So you have to add those last bit. 6 is 2. You're going to go then to 4, F14, and then 5, D10, and then 6, P2. Okay, and that'll fix this. You'll have 6s2 in your outer orbital, so 2 electrons, and then 6p2, so 2 electrons, for a total of 4 valence electrons. And you didn't box the valence electrons here, which you put a box around this and that. Okay. So just fix the lead, because I know you're going to lead on the test. You didn't finish. It's okay. Okay, so I'll wait till return periods. We're together a long time today. Yay. Okay, so if we refer to our notes, so please get out your notes from last class. The last scientist we talked about, if we remember correctly. Oh my gosh, I am so sorry, guys. Is it a cable thing? Is it a wire thing? Niels Bohr, right? talked about Bohr's planetary model. And then we split it up according to the sublevels S, P, D, and F. So I got a picture here to show you. This was last class. Let's try to go a little bigger. This is the shape of the 1s orbital. It's just a circle, right? So that is 1s. P orbital, so this is the P block. The P block kind of looks like this, at least in general. And then if you wanted to know what D looked like, you got this donut with these guys shooting out of it. So what are these shapes? These are locations where you would find the electrons in that sublevel. And then your F sublevel is like a double donut, double barbell kind of thing. Now, then in your head, you have to kind of put all of these together, right? And then have them moving. So because you can have an atom that has enough electrons to fill the part of the 4F, right? So if they do, they have all the prior sublevels kind of, and that's where the electrons are. So some pretty funky shapes for S, P, D, and F, right? And then this is just that kind of trick filling order thing you could use, but don't confuse yourself. You in no way have to use that. If you just read the periodic table from left to right, you'll be golden, right? If you just read, I don't know, guys, and my pen darts off to the side, right? I don't know, and the projector's way smaller. I'm really sorry, guys. Is this, how distracting is it? Is it terrible? No? Okay, thanks. So yeah, if you just make sure you read left to right across, you're going to do your S, then your P, then your S, then your P, then your S, then your D, then your P, then your S, then your D, then your P, then your S. This tells you F, D, P, S, F, D, P, right? So if you just read the periodic table like that, you don't need that little line loopy trick thing, right? So, so keep that in mind. Okay, so the history of the atom. It starts to get wackadoodle. It totally starts to get wackadoodle. So, and what causes it to get wackadoodle is this. Let me pull this over. Boo, boo, boo. Hopefully this will project nicely. Nothing like starting the morning with a cartoon. Let's try to, this really sets us up for everything you need, right?
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, They cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves,
Pay attention,
we get an
please.
interference pattern of many bands.
Joshua, please pay attention.
Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble.
Please watch the video.
So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So this is a pretty old experiment. Old in, the timeline we're talking about, it's the last, 75, 85 years. So really kind of blows your mind. So once that information came about and they looked at Bohr's diagram, well, this Bohr, so Bohr hooked up with de Broglie, D-E-B-R, capital B-R-O, I gotta get the names right, Broglie, because de Broglie was a student of this double slit experiment. And he said, hey, so de Broglie said that all matter, very influenced by the double slit experiment, all matter has properties of waves. Properties of waves. And hopefully it is just waves like you think of water. So all matter has property of waves. But de Broglie said the lighter, so the particle, or the lighter the matter, the greater the wave effect. Wave effect. Oh, guys, tell me when I'm writing off there. Greater the wave effect. So remember, electrons are like 1/5000th of a proton. So that's pretty light matter. So it kind of makes sense these two got together, right? So the lighter the matter, the greater the wave effect. Broglie, all matter has properties of waves. There isn't one person who did the double slit experiment, right? That's a whole group, many labs around the world. So it's not like, oh, this one guy came up with the double slit idea. That was an effort of all physicists at the time. And it influenced all the physicists from Bohr on. It influenced them all. So de Broglie embraces the whole wave idea, which is super cool. And one of my favorite names ever, Wolfgang Pauli. Wolfgang Pauli. Pauli, that's on your card. Wolfgang Pauli. He was like, well, remember when they thought the interference pattern, that the particles were bouncing off each other to create the interference pattern? So from that, he was like, okay, so no two electrons. So no two electrons within the same atom, right? So we're talking just one atom. Can have the same quantum number. And you're like, what? What kind of statement is that? So he's thinking that for them to actually act like matter, they can't kind of bump into each other and still create the single slit when being observed. Yeah. So he's kind of the collapse wave function. He's not quite embraced the whole, these guys are waves, but he is saying that the reason sometimes they don't hit each other is because there's not more than one in that location. So he's kind of bringing up, where exactly is the electron? Like, where exactly is it? Where exactly is it? So who comes along to try to answer that question? But first I want to show you a few pictures. Does anyone know who comes along to answer that question? Off-bow, that would be awesome. But well, off-bow also hooks up with Bohr, because remember our Bohr picture, it was about, and what we're doing next week, actually, I'm glad you brought this up. Remember, it was about energy levels, like the energy of the electron. So off-bow actually brings energy back to it. So he's going to come back. But I have a picture here I want to show you with my notes. So here's the thing. If this is what it would look like if electrons traveled as waves. Instead of being in this designated orbit, they would be whoop, 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 right? A wave. So this would be whoop, whoop, whoop. And now let's think back to the two electron thing. Let's think back what Pauli said. He's like, Well, if you have two, what's going to happen right here? They could run into each other, right? And they have these repulsive forces. So that's why he's saying that can't happen. You see why he didn't embrace waves? He was like, that can't happen. They can't be in the same location there, right? That can't happen. So totally, I mean, he's not, it seems like wackadoodle compared to everyone else, but give him a chance to explain and it kind of makes sense. So then I also pulled these pictures because what is his evidence that it doesn't make sense? Remember, if we have the rings and these guys are traveling in waves, you can see how the wave of the inner ring doesn't line up with the outer ring, but these two do and this one doesn't. So again, the repulsion factors here wouldn't work, but that's okay because maybe, see the difference between these waves? Like, because different waves can have different frequencies, right? Different wave crest and wave crest. So he's said, Paulie's like, see, this doesn't make sense. They're not going to be there. His prior drawing was a little more that you can't have two electrons in the same place at the same time. But the answer to that was maybe you can if they're not traveling in the same frequency, right? Maybe you can if they're not traveling in the same frequency. So, okay. Again, it's about where those electrons are. And I liked this picture because it kind of brought back energy. Okay. Here's one type of wave. Here's another type of wave. Are you guys in pre-calc? Yeah. So what are these guys? Have you gotten into sine? Right. So have you done derivatives and stuff yet?
No.
Okay, so you will. This will become. This will look very familiar in a month or two, maybe. I don't know when you get to it. But this would be the energy or distance from the nucleus and the behavior, right? So, okay, electrons are going to have different things. Well, the ones in the S, 1s will act like this. You know, 2p will act like this. 3d will act like this. So this is those different wavelengths at different levels to keep the electrons from being in the same place at the same time, right? So this is that explanation. This is, well, if they're like this, it will work. Well, then, lo and behold, turns out maybe the planetary model isn't that far off. There's tremendous evidence. Well, it is this way. That an electron doesn't stay the same distance from the nucleus. So in the second energy level, the electron, it will literally get really close to the nucleus and come far away from the nucleus, and get close to the nucleus and come far away from the nucleus. So that information is where we saw the S shape, right? But the P shape, you guys know this guy, what is it? X, Y, Z, right? The 3-dimension X, Y, Z. Like I'm trying to draw like something 3-dimensional. Does that look a little 3-dimensional? Right? So if this is where the electrons are traveling in their waves around the S, right? And not and if they, not two of them, because if it's two of them, then they'll have that place where they can't both exist. So that's where the shape of the S, so did you see that? That was the electron traveling around the nucleus. It comes close to the nucleus and then zips away. It comes close, almost like a comet in the solar system, right? Comes close and then whips away. And then that's that direction, but atoms are 3D. So it goes on the y-axis too, but atoms are 3D. So it goes this way too. right? Now, that's how those are traveling. This is P. This is going to tie in. How many electrons can P hold? 6. Okay, so P holds 6 electrons. So this is what comes up next. There are X, Y, and Z, 3 dimensions. We live in a 3-dimensional world, right? 3 dimensionals, X, Y, Z, 6 electrons. Hey, what if they travel in pairs? What if they travel in pairs? Then that would work. We're a 3-dimensional world. Those 3 dimensions, these 3 barbells, these shapes, the elliptical, sometimes further away, sometimes closer. So it's not the smooth elliptical, right? It's not that X, Y, Z. It's the little infinity sign. Does that make sense? So, okay. Well, if they're traveling in pairs, we go back to this guy. Pauli, no 2 electrons can have the same quantum number. Well, maybe they can. Maybe they can if they're not going the same direction. One's going one way and one's going the other. If one electron is going that way and one's going that way, and then you're like, what? Okay. And all the scientists were like, what? Okay, no. I'm not saying that one electron is traveling this direction and one electron is traveling right for it, right? Not saying they're going in 2 different directions. They're spinning in 2 different directions. So now we've taken the particle and we're literally spinning it. Now, I don't know how much physics you've had, but why is a good football spiral what you want when you throw a football? Well, it's going to go straight and it's going to go further, right? Because you can throw it where it's not spiraling. But if you can get it to spiral, anything spinning in the air goes a lot further, right? Less resistance, less energy, all of that stuff. So this is actually favored in the universe. It's easier to spin and travel through space-time than it is to not spin and travel through space-time as little particles, right? And bullets in the rifling, what's called the rifling of the barrel of a gun, is literally like this. So when anything gets pushed out through it, right, it's spinning. Right, so it's actually spinning, which is, it's nice that they applied physics to something that kills people, but also that's why I always think that's why the ping pong launchers aren't as good. We need to rifle the ping pong launchers. Yes.
So in theory, if we were to ever actually try to make something to move fast enough to basically go to light speed, we have to make it spin.
Mm-hmm.
Which basically just came to my mind as thinking basically from the Lightyear movie. Instead of just the spaceship, it was just spinning in circles, and I don't know why.
Oh, it was spinning to make gravity.
I know.
I
just imagine the spaceship spinning in circles as it's flying around the sun.
Oh, okay. So hopefully this stuff is kind of starting to fit together, right? Like going, oh, that kind of makes sense and that kind of makes sense. Okay, so they're spinning. Pauli says no electrons can have the same quantum number. Well, okay, could they if they were spinning? But we still have the big question, where are the electrons actually, right? So SCHR, oh, anyone ever heard of him? Schrodinger. You probably know him because of the next picture. This guy. Yeah. Schrodinger's is a bit of a potty mouth. Never ask him about a cat because he's cussed out many people because he's very upset that his life work was brought down to Schrodinger's cat. So just letting you know, he died in the 60s, so we really couldn't offend him, but let's honor his, we're not just going to know him from Schrodinger because he did a lot of other stuff, but let me explain the cat thought because it kind of ties into the observation of that electron as it goes through the slit. Okay. So this is radioactive something, right? Well, it's basically excited electrons that are going to fall down. Excited electrons that are going to fall down. And where they fall, completely random. So it kind of even hints to entanglement. You know, like something on the East Coast affecting something on the West Coast. And they proved entanglement. Do you know about entanglement? Amazing experiment. The electron spin on the East Coast will force the opposite electron spin on the West Coast. And the matter's nowhere near each other. They're literally entangled through the space-time continuum. Right? The chemistry your kids learn is not what you're learning. It's going to be something totally different. But with that idea, you have a cat in a box and you don't know which way the electron's spinning. Right? If it's spinning one way, cat's alive. If it's spinning the other way, cat's dead. You don't know till you open the box, till you observe it, and it forces it. So before you observe, it exists as both a living and a dead cat until you open the box, right? So an electron exists as both a wave and a particle until you observe it, right? Now, what if you kind of don't really look, but you kind of still paying attention kind of thing? Well, then it's going to act as a wave and a particle. If you don't really look and you're just kind of paying attention, then the cat is both alive and dead, and there's entanglement that occurs. I know, blows your mind. So Schrodinger, he doesn't like being known by the cat, but that's the cat idea. He completely, more importantly, and well, he was a color theorist. He was into psychology of color. My purple, is it your purple? Is when I look at something and the wavelength of light that hits my eye and I go, okay, that's purple. Is that what you see? Is that your purple? Right? So he was, that's what Schrodinger actually loved. And that's what he spent most of his life doing is psychology of color theory, right? But just a little side shoot was this whole quantum nonsense. But he came up with a mathematical explanation so back to math of how you cannot know both the location and direction of an electron at the same time. So as soon as you can calculate where it is, as soon as the math shows where it is, then its vector, its direction and speed can't be known. But you could calculate the direction and speed, but then you can't know its location. So that leads to Heisenberg It's like, okay, people aren't going to understand that. Heisenberg uncertainty principle. Uncertainty. Have you heard of that principle? Heisenberg's uncertainty principle. And this is an on. I'm sorry about that. Do I need to white out that? I can. Heisenberg's uncertainty principle. It didn't really help, but it did it. There we go. That's a U, uncertainty principle. Which is restating you cannot know an object's exact location and speed at the same time. That includes you. That includes you. So ultimately, all of these scientists that we've talked about, all of them ultimately came up with the quantum mechanical theory of the atom. So quantum mechanical theory of the atom. And this is where your child's, this is where our timeline or thing ends at the quantum model of the atom. But it'll be in the middle of a timeline in the future because the quantum is gonna, you know, keep being expanded. Make sense to you guys? Now, again, with the scientist, you don't need to know dates. You really just want to try to understand what did they know, and it made sense that they thought what they did from what they knew before, right? Because they didn't, you can't see into the future. So if you can just kind of remember what they knew, a couple things you will have to be able to kind of regurgitate for a test is Rutherford's gold foil, right? He did the gold foil. So tie those two names together in your head. Thomson and the plum pudding, tie those two names together in your head. The Bohr model, tie that in your head, right? Now, Pauli. So today, let me show you one more thing. So now we're going to get on to what we're doing today. This is a harmonic oscillation. Let me make it bigger. I didn't know I could make it wide like that. Of two electrons, them traveling in pairs, right? Just straight from, and this is evidentially determined that actually if they are traveling in pairs with opposite spins, it's actually more stable. And then you see the times that they overlap, right? That we thought could not happen. Well, that's when they're acting like a wave and not a particle. So can a wave be repelled by another wave? Remember, interference patterns were the black spots, right? They didn't show up. So an electron, kind of freaky, is a double slit experiment. Opposite spins traveling in pairs in wave function. When they have that little node thing, they're not particles anymore, they're waves, then they go back to particles. So that explains it. That explains it all. So we're going to turn the electron configurations that we learned last time. And now we have new information about traveling in pairs, being more stable, opposite spins, and we are going to draw orbital diagrams. Orbital diagrams. It's going to be fun. It's going to be fun. You're going to learn how to draw orbital diagrams. So, once again, thank goodness. I don't have to draw. Take one, pass it around. Let me see if I can beat you. Have your card ready. Yes, that's what I said. You're getting ready to learn that right now. People here take the bus. Take the bus to school and home. How many people in here have never been on a bus? Like in general. You've never been on a bus. For field trips, you have. So, has anyone never been on a bus? Okay, super cool. Because there's something called the bus seat rule, and it's a nice analogy, but I just wanted to make sure. Everyone have one? Yeah, cool. So, orbital diagrams. We're going to look on the right-hand side right now of your, oh, I don't need a whole stack of them here. Look at the right-hand side right now. Oh, again, sorry for this. Move that out of the way. It's like the blue part knows what's on the screen, right? Like, I don't know what that's doing. We have increasing energy here, and hopefully you're seeing some stuff that looks familiar. Yeah. Now, you have your card with you, I'm presuming. I want you, oh, I'm going to have a different color card. With your card. We're going to travel from the 1s level, which is towards the bottom of the diagram, right? The bottom of the diagram, right here, the bottom of this diagram is the nucleus. The nucleus is like right here, okay? That's how this works. And I'm going to slowly move my card up. Slowly move my card up. So I've covered 1s, and as I move my card up, I cover 2s, and then I hit 2, I cover 2p, then I cover 3s, then I cover 3p, and now I cover 4s, and then 3d, and then 4p, 5s. After 5s, 4d, then 5p, 6s, and then look where 4f is, right? So I'm going up the y-axis, right? I'm going up the y-axis. So 7p is the highest energy, highest potential energy, energy of position. Think of that ball high on a hill, right? Energy of position. So down here, closer to the nucleus, these electrons have lower energy. Makes sense to everyone? What electrons? There's no electrons there. There's a line. Couple rules. electrons travel in pairs with opposite spins. We are going to represent those by half arrows. Half arrows. A half arrow is you go up and you only come down one side on the top of the arrow. You don't come down both sides, just one side. That's a half arrow. If I have a half arrow going in this direction, I cannot write another half arrow going in that direction, right? That's not opposite spins. So my next one has to be going in this direction. Well, a half arrow equals one electron. Half arrow equals one electron. So as this is written right now, this is 1s2 because there are 2 electrons in the s sublevel of the first quantum number. Right? Now, these electrons have the lowest energy because they're close to the nucleus. Everyone with me? Coming up, can you tell me, well, first, can you tell me what element this is? Helium, right? Because 2 electrons, there it is, helium. It's helium. So if I added another half arrow to 2s1, what element am I? Lithium. And then I go, what element is that? Beryllium. Now, Hund's rule. You have a card. Hund's rule. If you envision this as, I don't know, here we go. This is my bus. Okay, here's your bus. Think of this as a bus. These are seats on a bus. When you get on an empty bus, you sit on a seat, right? So electron does the same thing. Not a problem. Someone else gets on the bus, they're not going to want to sit with that person because they don't know them. So they're going to get and sit on the next seat. The third one comes in, doesn't know these 2, so they're going to sit on the next available open seat. Make sense? So when electrons fill the p sublevel, remember this guy, XYZ, we have one traveling this way. That's your first seat. The next person to come in does not join this guy, right? He goes, okay, well, I'm going to travel in this direction. And the third one that comes in doesn't go with either one of these, says, okay, well, I'm going to travel this direction. So these are half-filled orbitals. One's going in the X direction, one's going in the Y direction, one's going in the Z direction. Hund's rule is called the bus seat rule. Electrons are not going to pair up until they have to, because you'd rather have your own seat, right? And you don't know each other. So what element is 1s2, 2s2, 2p3? That's 3p3. 2p3. Nitrogen. Nitrogen. So what does oxygen do? I need to add another electron. I'm not going to pair up till I have to. Right? That's the only place I go. Not going to pair up till I have to. Not going to pair up till I have to. So Hund's rule, electrons, however you want to say it, they won't pair up till they have to. Electrons will occupy all empty seats. I'm going to replace the word seats with orbitals before pairing. So that's Hund's rule. Put it on your card. Electrons will fill empty orbitals. This is a shout out to Bohr, right? His orbits. Will fill empty orbitals before pairing. Pairing up. So, well, what is it? Okay, we're going to stay with that. I'm going to define an orbital in just a second. Okay. So, quick question. If you were to, just like yesterday, when you had to pick out the wrong configuration, right? If you saw, boom, 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 boom. This is my P. Oh, geez. That's my P. Boom, boom, boom. Is that right? No, that's not right. What rule is it violating? It's violating Hund's rule. Okay, so multiple choice question, which of the following violates Hund's rule? And you'd be looking for the arrows. You have to know Hund's rule is, oh, they sit by themselves first before they pair up. So since there is an empty seat, an empty orbital, that guy should not be there, right? So I'm going to be able to recognize that error. So that's Hun. What's the next one? Off bow. Off bow. Remember, here's the nucleus. I am so sorry. This looks so horrible, but you know what? I'm going to take I took a little video. I'm going to take a little bit more of a video, and I'm going to send it to the IT guys and not know what you guys had to put up with. I'm really not in a bad way, but like beg them to help me fix it. So remember, the nucleus is here. So if off bow said that electrons fill lower energy levels first. Now, some people have referred to this, and if you look online under AFBAL, a lot of times you'll see an apartment building. Because if you go to rent an apartment, I don't know, and you're a grocery shopper and you love grocery shopping, you're going to rent an apartment on the lower level before you'll rent the next one. I don't know if that's true, but in the past, I guess the lower the apartment, the more coveted it was. So often off bow is like the apartment building rule. When you go to rent, you won't fill the next one till this is all full. And then you will go to the next one, and you don't jump to the next one till this is all full. But I don't know if that holds true now. So violating the off bow would be if I'm in pairs, go in an opposite direction. That works well. But then I even follow Hund's rule. But this violates off bow because I didn't put anything here. Remember, you travel from the nucleus up, and that. Can I get the blue thing to go away if I just write on pink? No. That was exciting, wasn't it? I was like, now it's not going away. Okay, whatever. Off bow rule. Electrons fill lower energies first, so you can't jump to a higher energy until the lower ones are full. So then the last one is what? Pauli. And what was Pauli talking about before? Wolfgang Pauli, they can't have the same quantum number. Well, It's often called the Pauli exclusion principle. Basically, I'll show you a violation of the Pauli exclusion principle, and you see if you can figure out what it is. Okay, can't do that. And too many in an orbital, they travel in pairs, not triplets. And they can't have the same spin. Okay, so electrons cannot have same spins in same orbital. And remember, he was all about no two electrons, and basically they travel in pairs. Well, that's not a good way to say it. They pair up. Or two electrons maximum amount an orbital can hold. So now, what is an orbital? Let's look over at this diagram. Here, this is where we start. So this is kind of not an energy orbital diagram. This is more of like just the sentence version of an orbital diagram, writing left to right, top to bottom kind of thing. So an orbital is this box. An orbital is that box. If we want to get a little more graphic, and we look at our notes, traveling in X, let me pull X out of here. That is an orbital. This path is one orbital, right? So whatever electrons are in here are represented by a box. And then the Y, this guy, if I pull out Y, it's going this way, right? So we have our X, our Y, whatever electrons, which we know, according to Pauli, has to be two and they have to be going in another direction. This is an orbital represented by another box. And then we have our Z. If I pull out Z, that's where two electrons are likely to be found, Heisenberg uncertainty principle, and that is represented by a square. So if I look over here, this whole thing is the P level, and there are three orbitals in the P level, right? Goes to the shape. How many orbitals in the S level? One. And remember, the shape is just a circle, right? The P shape was a little different. S, again, little circle. P, the P level has three orbitals. Now, what does the D level have? 5 orbitals. It can hold 2 electrons each. Those are the 10 electrons that we've been counting in our electron configurations. So are we seeing how this is kind of tied together? So super quick, why don't we continue this? And I'm going to say potassium. Please finish this one doing the orbital notation of the potassium atom. Question, yes. Pauli exclusion principle. Yeah, I'm gonna put it up on the card too, right? Off bow. Thank you for reminding me. Lowest energy levels filled before energy. And then poly. And orbital. And only two electrons of opposite spin. Yes. Yes. Absolutely. Okay, so I'm gonna do it off camera. 1s2, 2s2, 2. How'd you do? Yeah. So if you just counted up, you look at potassium, it has 19 electrons, and you follow the rules, starting from the bottom, 1 electron, 2 electron, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Right, just counting up. Now, knowing what these are called, what is, from an orbital diagram, what's the electron configuration of potassium? 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. What is the abbreviated or noble gas configuration of potassium? Argon, nice. Square brackets, 4s1. How many valence electrons does potassium have? 1. And where is that located? 4th energy level. Yeah. Kind of cool. So you are to, we have now doing it this way. Let's try this one. Let's do a hard one. Let's do copper. That's not a hard one, but copper and this is already in order according to energy. So you're straight up. Yes, they have to be half arrows in the boxes. Good question. Three, 2, 4, 5, 6, 7, 8. How'd we do? Or how did I do? So it is a good habit. So the bus seat rule counts for the D and it counts for the F. It is a good habit while you're filling it in to just follow that rule. Put one in first and then fill in the other, even if you know it's full. It's just muscle memory. It's just muscle memory. It's a good habit to get into. So my idea was you have 1, 2, 3, 4, 5, 6 elements to do. Okay. Would like you to make a word. It's one of the best things the periodic table is good for, right? You can make words like thallium, indium, and potassium. Right? You can make words with the element symbols. So in your 6, I would like you to make them all be in a word. It could be 2 words, 3 words, all in 1 word, if you can have a 12-letter word, but pick elements that make a word. It's a fun part of the periodic table. It's practice. Maybe try to make your name. Can you make your name with the elements of the periodic table? One down.
Wait, where did you write the?
I did.
No, it's a word. You said like.
Well, you can come up, what are you doing? Is that your work?
No.
Oh, so you can write it. I'm just gonna look at them all and it needs to make a word. Or 2 words, or. Try, you can always try your name. So what's your last name? What about parts of your name? Oh. You have to wait till it's right there.
But yeah.
I appreciate that. Be ready.
What did you say?
Yeah. Bacon, you can do different ways. You can use cobalt or carbon and oxygen for bacon. Bacon's delicious.
But like bacon's with the S side and not the S.
Bacon's? Should be, because no one has just one bacon. Hard to eat just one piece of bacon. Yeah, sure, bacon's is the word. Why not? Can I do that later? Now you're better. Okay, so let's check it out. Okay, so we did these together. And this is.
Yeah, that's two.
Yep. So these are the valence electrons. Carbon, one, P1. Yeah, because you're in the second period. Nitrogen.
It's the little ones on the.
Yeah, that's only one B block. Two.
Oh.
F,
Wait, there's no
5, 6. One S2, two S2, P6, that's here.
No.
Three S2. Chlorine. So. And P's, you're not, it's not consistent, right? Or no, it is just the P. Now then, for the, okay, so lead, coming here, right? One is two. One is two. Two is two. Yeah. You know what you're doing, you check the back. Right? Yeah, you just told me what. That's not an easy thing to do.
No, we'll do that. Looks like.
That's a bonus. That's not a word. Just who said Make sure your card's good to go, especially for the quiz. Remember, you can use your card on the, you can use your cards on the quizzes, the quiz. You didn't finish. You're not getting- The date of the quiz, the date of the test is on the calendar in school. And what it's saying. Very. So you have to, this is a bus. And you're Molly Benham. So Molly Benham is 484. No, it could be 2 words. Like boo cow is 2 words. Wow. Right? You were about to make this. So we can just.
Oh, yeah. Oh, yeah.
I just got it.
Hydrogen, oxygen.
How?
I did great. So it has like radium.
Oh, wow. You okay with that?
Wait, what's that? That's CO, and then.
People make all kinds of words.
I'm just gonna do carbon dioxide.
That's a class word. When I passed out in your home. Yes. So I passed out the finding the words. I also passed out a table for just extra practice, but that will be what's on your homework. That's what I'll check for the stamp for homework. So the chart below. Number alpha poly indicate the number of unpaired electrons for each element in the last row. To do that, you're just looking for the arrows. You're looking for the arrows that don't have a pair when you're done. They have pairs, they have 0 pair, sulfur, CDs don't have pairs, 2 unpaired electrons. And they show 1 and 3 unpaired Oh, okay. It's just some more practice, but it's asking you valence electrons again. How many valence electrons? How many unpaired electrons? Those would be the ones that an arrow in an orbital without another arrow. So the paired electrons are in the box house.
Wait.
Yes. What?
That all of that.
Oh, maybe I should just use this as a document camera. Wait a second. Are you kidding? Hey guys, I fixed it. I think I fixed it.
I managed to figure out a funny word that actually works.
Okay.
Lucifer.
Is that a funny word?
It's funny that it works. You have to admit, it's hilarious that that actually works.
Yeah, I'm not a fan of Lucifer. Or, well, I shouldn't say fan, but no, it does. Yes, that is a straight up name, and you didn't have to change anything. Spelt correctly, I think. It's hard to tell. Can you find Beelzebub?
I don't even know how to spell that.
Beetlejuice? No, there's no J, right, Jacob? Why didn't I name my kids using the periodic table? That would have been helpful, right? Yeah, I could have totally picked an element name. Xenon, it's time to go to bed.
Sorry, or dramatic. Sorry.
Yes.
This one, unpaired elections, do you want us to just put 1 or 0?
So when you draw, that one doesn't have a pair.
Yes. So what would you write in there?
That's
Would you
an
write
unpaired,
1?
yeah.
Just 1 or 0?
Yeah.
For each one?
When, no, you might have more than 1 or 0.
Oh, like if it's, yeah.
Nope.
I don't know. We're thinking about the same thing.
Let me make sure I put Dr. Quantum. Oh, wait. Let me make sure I put Dr. Quantum in bed in Schoology, in case you guys want to watch that again.
What'd you do? Bake is.
No, it just has to be like 1 or.
Bacon is awesome.
Yeah.
You know, no one's doing a bacon project this year. So I guess I'm just gonna have to scan in my handwritten notes for Schoology.
Yeah.